Oh, hello everybody for the second session of Multiphase. My name is Henrik Rusche and I will be your chair for this session. Unfortunately, we have a no-show for the first speaker, with the pleasant surprise that we can give more talk time to the other speakers. So we have time for plenty of questions, and I hope to receive them, and we'll read them obviously to the speakers, and we'll do the questions after each of the talks as usual. So our first speaker is Tobias Tolle from the Technical University of Darmstadt, and he will give a presentation on the initialization of volume fractions and signed distances on unstructured meshes from triangulated surfaces. Tobias, the floor is yours.
All right. So can you see my slides now?
Perfect.
All right. Thank you very much for the kind introduction, Mr. Rusche. The method I'm going to present to you in the following is joint work with my colleagues Dirk Gründing and Tomislav Maric, and also Professor Bote from the Mathematical Modeling and Analysis Group at the TU Darmstadt. Let me first provide a little bit of context in the actual problem statement. In the context of two-phase or multi-phase flow, we have the situation that our problem domain, shown here in the picture, is divided into several subdomains which are occupied by either one of the phases. For example, here like shown like this gray droplet surrounded, for example, gray water droplet surrounded by air. And if we want to initialize such a setup, we need to also to provide the initial conditions for the distribution of these phases. And if you, for example, use the quite popular volume of fluid method, which uses so-called volume fraction to represent these phases, we need to initialize them too. However, what one usually has provided at the beginning is not this distribution of the surface of the volume fractions, but instead the actual surface here named sigma. So the question is how to compute the initial volume fractions from a given surface sigma, and how to do this accurately. And of course, this depends how the surface sigma is actually given. This can be in the case that it is given by an explicit or implicit function or a composition of multiple such functions. Then there's a variety of methods available in the literature. Some of them are limited to certain cell types, for example, Cartesian cells. But this is state of the art, I would say. However, what's in the case when the interface is given as a triangulated surface, as shown here in the picture in blue? We have an example in our work group. My colleague Mathis Fricke, he wanted to simulate the breakup dynamics of capillary bridges and wanted to compare this to an experiment. And from the experimenters, they provided him this blue surface as an STL file, and he recognized that they had no tool at hand or not even a method to compute the volume fractions from this surface file, which was quite puzzling because with triangulated surface, you have a very high versatility on what kind of surfaces you can approximate. And also many software packages support file formats like the STA, which has safe triangulated surfaces. And this is where our method comes into play. The input required for this method is which is important, is that the surface is oriented, so meaning that the normals provide some consistently point to one side of the surface. And here in an overview, we see the three, so to say, fundamental steps of the method. We first need to establish an efficient search structure. This is done with an octree. this octree is used to efficiently find for mesh points the closest point on the surface mesh. In the second step, we use this search structure to actually find the closest points to the interface and compute signed distances, and also to propagate this information from the vicinity of the interface to the bulk. So if one is interested in signed distances, one can just stop after this step B. But if volume fractions is what is required, then in the third step, we use the signed distances to actually compute the volume fractions in the cells. So I will skip the octree part. This is we reuse from OpenFOAM's indexed octree class. But let's come to the signed distance computation. So for some mesh point X, we, for example, this one here, the octree provides us the closest point on the surface mesh. So this is the absolute distance, just the Euclidean distance between those 2 points. More interesting is to correctly set the sign with respect to the orientation of the surface. If the closest point is actually on a triangle, like here, we can directly use its normal orientation or its normal. However, this does not work as the closest point is a vertex here. We solved this by actually first computing normal informations at the vertices, and then use linear interpolation between the vertices to find or to compute a normal at the closest point x min. And it turns out this gives us a very robust inside-outside classification. Maybe note on computational times. For efficiency reasons, we compute or geometrically compute the signed distances only close to the interface, but not far away in the bulk. So as a next step, we need to actually propagate the inside-outside information to the rest of the domain. And this is done by computing an approximate solution to a diffusion equation where we use Neumann boundary conditions. And we set the initial field to either to the computed signed distance where it's available and 0 otherwise. And with just a few iterations of an iterative linear solver, for example, with conjugate gradient, we get the relevant information, mainly the sign here. And with this information, we can start to actually compute the volume fractions. First, we set them in the bulk according to the sign of phi, to either 1 or 0. And so you can see this is correct, of course, in the bulk, but not for the cells which are actually intersected by the interface. And these we correct in a subsequent step, either by performing geometrical intersections between the cell and the triangles, or by using an approximation procedure together with tetrahedral refinement. Here we'll just outline briefly the details of the approximative procedure. We first identify those cells which might be actually intersected by the interface by computing bounding balls. These are decomposed into tetrahedra, depicted here as triangles, and further refined until a suitable decomposition is found. And then we use a model by proposed by Detriche and Aslam, which gives us from the signed distances at a tetrahedron, gives us the volume fraction, so we can actually compute with this the so to say the gray area in the tetrahedra, sum this up, divide by the cell volume, and we get a volume fraction in the cell. So that's the algorithm. Let's have a look at some results. Let's start with a rather simple surface with an ellipsoid in a unit domain. We have looked at the relative global volume error between the volume given by the initialized volume fraction field and the exact volume of the ellipsoid. We have done this for the resolutions of 16 to 128 cells in each direction. And here on the x-axis, you can see the number of, or the square root of the number of triangles. And you can see that both for the approximative algorithm and the one using geometrical intersections, we can achieve second order convergence with respect to the surface resolution, which is nice. So let's move to a more complicated test case, something like here with this lesson, so to say, an exemplary cat geometry, for example, which has a non-smooth or approximates a non-smooth surface with kings. We have here the surface mesh, and on the right-hand side, the signed distances. And we can see here that the inside is, so to say, the positive part of the domain, and our method robustly computes the correct sign or classifies as inside and outside. And if we compute from this the volume fractions, we get a global relative volume error of in the order of 10 to the power of -6. Some further showcases of even more complex surfaces. For example, we have here the surface mesh of something which could be a porous media. And on the right-hand side, the volume fractions that have been calculated from this. And we can see the resemblance of this volume fraction field and the original surface. Another showcase here is a surface I just got from Thingiverse with rather bad surface mesh or mesh quality. But still we get an accurate volume fraction field with no false cells on the outside of this body. So to summarize, we have developed a method that can compute or initialize signed distances and also volume fractions on any mesh type that is supported by OpenFOAM. As an input, one needs a oriented triangulated surface. This can be an STL file or a VDK file. We achieve good absolute accuracy, and we also have second order convergent with respect to the surface resolution, which was or to be expected since we use a piecewise linear approximation, and which is also nice. The computational times are low. The cases shown here, they have all been computed in serial, and none of them has taken, I think, more than 2 minutes to initialize. If you want to know more about our method, there's a preprint available on arXiv and also an open source implementation, which you can find on GitLab as part of our Argo project. And of course, feel free to directly contact us. With this, I would like to thank you very much for your attention, and feel free to ask questions.
Yes, thank you very much. I'll do some clapping to just make sure that we don't lose contact with the real world. Okay.
Thanks.
You've got a number of questions, which is good.
Nice.
So the first one I'll read to you is, thanks for the nice talk. Just as an idea, couldn't snappy hex mesh used for this task? Then you maybe end up with a closed volumetric phase zone where you could set your desired volume fractions.
Actually, I have not thought about this, but this might be that I'm usually not, I have actually not used snappy hex mesh yet, because yeah, we're usually concerned mainly with droplets or simple droplets. So so far I've only used the block mesh mesher. So I would actually need to look into it if this would also be possible.
Mm-hmm. Okay, so I'll have the next one for you. Nice talk. Have you thought of using phase field method to compare your results with WOF? Also, is the interface sharp in your approach? That's a real one. That's a good one for you.
So far, yeah, the method I introduced is actually just for initialization, because if you go like the example I showed in the beginning, if you move away from simple surfaces, you usually end up with some kind of triangular surface. The example I've shown, this came actually from Surface Evolver and was a minimal surface. And it was just a question, how do we get from this surface mesh volume fractions that match, so to say, this surface? And this, after this initialization, so to say, our part is done. Then from this, my colleague continued with the actual VOF simulations. So this is just about initialization at the moment.
Yeah, I don't think really your plan was to ever have a sharp interface. I mean, at least for WOF, you wouldn't get such a thing. Yeah, and it's never 0 and 1. And with some cells, you're never going to match the volume. Yeah, so you must have some cells with fuzzy volume fraction.
Yeah, I mean, this is part of the VOF method that you have. I mean, if a cell is intersected by the interface, then you will get something between 0 and 1.
Yeah. Yeah. So I wouldn't see that this is a goal to have it sharp. I mean, define sharp, but yeah. Okay, so the next one, really interesting work there. I often face spurious current effects when I use WOF methods. Will the approach influence that in any way?
That's a really good question. Actually, that is something we want to look into now, because we're in another project, we're also looking at some simulations which are on a small length scale, so their capillary forces will play a crucial role there. And this is something we want to do in the near future to just initialize a stationary droplet with different accuracies and see if this has an effect on the temporal evolution of the velocities. So open research question, I would say.
Yeah, but then you would have to bring it inside of your simulation, yeah? I mean, as a sort of reconstruction method, or what is the plan there? Because at the moment you just do initialization.
Yes, but then we would go, we're actually, I think for this project, we're working on with inter-isofoam in this case. Mm-hmm. And we would then just use our method to initialize, in this case, actually from an analytical sphere to initialize the droplet and use this volume fraction field as initial field start. And if this field has a different global errors, we can then see if if it has any effect on the evolution of the velocity field or not.
So the next one is nice talk. What kind of experimental validations are attempted?
Actually, there is not. I think there is no. We actually do not need, or for the initialization itself, it's since it's in the end just a geometric problem. We have not planned any experimental validation, because we can just use, as shown in the picture for the graph for the ellipsoid, we can prescribe exact analytic surfaces, mesh them, and see what we get in terms of the global volume error there.
Okay, thank you. And I have one more, or actually a couple of more, and we have much more time here. So one from Lionel, very interesting talk. Where did it go? Up here. On a single sphere case, have you compared your results to set alpha field utility? So probably that is the worst case scenario that you can compare with.
Not yet, I have to say. This is also something we actually want to do as part of the comparison, where we want to look at the different initialization accuracies. We also want to compare to the set alpha field utility and see if there are differences.
Yeah. So this one can go. Here we go. Hello, thanks for the nice presentation. What was the time for simulation?
So
I think it depends on your cases, right? And the number
yes,
of triangles.
But yeah, so far we it was just to to clarify or emphasize again, was just like setting the volume fraction field. And for example, this let me go to this for example, for this case here with around close to 700,000 cells and 100,000 triangles on a single core. This takes around, I think it's less than 2 minutes to compute the volume fraction and the sign distances.
And I guess this is all serial, yeah? So you didn't bother making that parallelize?
Not yet. This is still work in progress. I think most of the parts should already work in parallel because we only rely on, I mean, these are mainly cell local operations, or either we rely on parts which are from OpenFOAM and should already be parallelized, and the actual procedure to compute the intersected cell volume fractions, these are cell local. So it should be a small step.
I think your solution is walking kind of spreading out the sign thingy.
Yeah,
that's probably where you have to do some work.
Maybe. Yeah, but this is done. We use the linear solvers for use the.
Oh, that is good. Then you have no problem.
Yes.
That will work. Okay. Good. Any more questions? Because I'm running out of questions here. I was just wondering, I mean, at the beginning when we have some time, so I can chip in some more questions.
Of course.
So I was thinking, do we do it geometrically? You could go for something like OpenSCAD or something like that, yeah? And just, I don't know whether you're aware of that, but it's basically a cat kernel, and you can load the STL into that, and you can do the intersection, and that will give you volume fractions. And I assume it's going to be exact sort of. But then I would guess that is going to be quite expensive, because you have to make a little CAD model of each of the cells, and it's maybe not really the way to go. But
actually, this the idea with the whole project was actually started by my colleague Tomislav Maric, and he was, so to say, developing a library for these geometrical intersections as part of a geometrical unsplit VOF method.
Mm-hmm.
And this came up to him just as an idea how to reuse this his geometric library. And so he actually started with this, cutting the cells, and this actually works quite well. But there's always, in his experience, there are always some corner cases where also floating point accuracy comes into play. And as long as geometrical intersections work, it's fine. It's very accurate. And he also paid attention to that it's computationally efficient, so it doesn't take much time. For example, here, this ellipsoid case, it takes about 20 seconds with the finest resolutions. But there are always some, I guess if you would take real-world geometries, it's always a danger that something still goes wrong in this geometrical operations. And this will then in the end introduce, for example, spurious volume fractions, so that you maybe get like small satellite drops close to your surface due to this. And which will cause then problems in the simulation.
So you got one more?
All right.
Hello. Do you plan to expand the tool to allow initialization of velocity or pressure inside the STL?
At the moment, we do not have plans for this so far. But I'm not sure. Maybe one could. What I have thought about was to extend it so that you can actually say store cell sets, which may be then used together with set fields. Yeah, so far we just we are only interested so far in the volume fractions and the signed distances.
You will need to do something, but you have the volume fraction, yeah. So anything that is volume fraction larger than something, then you can do something, but it's not going to be. It's just going to be, yeah, whatever, yeah.
Yes.
Okay. I think we'll leave it at it. We are running out of questions, and I'm sure that our next speaker is already gearing up. So that would be Federico Monici.
Bye.
And he will talk on the solution of the Cahn-Hilliard equation in OpenFOAM, coupled and segregated algorithms.
Oh.
So the floor is yours.
Thank you for the kind introduction. I will share my screen. Right. Should be. So can you see my? Oops. Can you see my full screen?
Very well.
Very well. All right. So I'm Federico Monici from the University of Nottingham, and this talk is a way, let's say, a couple of ways that we can employ to solve the Cahn-Hilliard equation in OpenFOAM. Now, this work has been done together with other people, my collaborators, Matteo Cardi, Mirko Magnini, Ismail Mellas from the University of Nottingham, and supported by the EPSRC and ERC, basically all grants that I was working in while I was developing this. And a special thank, I want to thank Olga Marshall for the many nice talks we had and the inspirations, and Giovanni Giustini from Imperial College of London for again for many discussions and test cases we ran together. So what is this about? It's about the Cahn-Hilliard equation. So the Cahn-Hilliard equation is it's an equation that looks quite similar to the alpha equation in the form. The main difference is that there is an additional term, the divergence of a flux, which is calculated based on free energy for a chemical potential. So the derivative of the free energy with respect to this C field, which is normally called the order parameter, which doesn't necessarily vary between 0 and 1, it can vary between -1 and 1, it can vary between whatever, different values. And the bounds of this field, normally they represent different states, different phases. But the concept of phase in phase field is a bit is a bit broader than we normally think. How we normally think it in multiphase. So now this is a particular form of the Cahn-Hilliard equation where I choose to have a double well potential in my free energy, represented like this. And this form of the double well potential is not unique. Now it's perfectly symmetric double well, but it could be also asymmetric. But it's the main applications for this are multiphase flows and separated flows. Then this is the proper potential to use. And substituting this expression for the free energy into the Cahn-Hilliard equation, we get a fourth order equation. So with a fourth order Laplacian. So that is a quite complicated operator to solve in a general code like OpenFOAM, where you have second order accuracy, you have cell neighbors connectivity, phase neighbors connectivity, and you don't have large stencils. So why using the Cahn-Hilliard equation? Well, the Cahn-Hilliard equation can model a wide range of systems. It's been used to model systems in biological applications like cell growth. It's been used in multiphase flows. It's been used for modeling the formation of rings in planets, or the formation of planets and stars. And therefore, it's very versatile, and it incorporates the effects of the interface within the equation for the order parameter. So we have the free energy also contains the terms an energy density related to the interface. So surface energy density, if you want, that is minimized by the Canadian equation. So jumping into the numerics, a first approach that is often used, especially in finite element, is the so-called mixed formulation, normally solved using block-coupled matrices. So this can be done in OpenFOAM, especially in form extent. It's quite straightforward. So you define a chemical potential, in this case psi. So capital psi is the free energy, and the functional derivative of capital psi is small psi, so the chemical potential. And you just assemble a single block-coupled matrix. You are putting the time derivative in the upper left block and putting just one in the lower right. So it's a kind of, you have this Laplace operator of diagonal. We can also do it differently, actually. We can move the Laplace operators into diagonal of this block matrix, but I found it to be a bit less stable, likely due to the diagonal dominance. And I found that this configuration actually works well for all the problems I tried. Another thing you see in this matrix is the way in which the nonlinear term, so the double Y potential, is discretized. Now, it's not necessarily discretized like this. Actually, I wrote it, the way in which I wrote it here might be unstable. But you want to take a term, for example, this -1 here, that will be minus C. You want to put it on the right-hand side and keep it explicit, because it just you can lower the coefficients for your matrix, even if it is a block-coupled matrix, so it's a bit different thing. The method is quite robust, except for the fact that it might require quite quite a large number of iterations to solve this, to invert this matrix, and the preconditioning might be complicated because there are basically two different equations. So you need different preconditioning, especially if you have advection. And of course, in order to have the linear term converging, you need multiple iterations. So in the end, you need to iterate multiple times, especially if you want large time steps. So another approach I came up with is what I call the dual matrix approach. So in this case, the chemical potential is not really necessary. Let's say you can see the chemical potential as a nonlinear operator that acts on for the parameter C, and representing it in semi-discrete form, you can represent it as a matrix that multiplies C plus other nonlinear terms that are all kept explicit. And then from this, I perform the classic A and H decomposition that you can do, that OpenFOAM is using continuously. So A is just the diagonal, the vector containing the diagonal elements of the matrix M. And H contains the product of the off-diagonal terms with the C vector. So what are these M and S about? Well, M contains everything you want to keep implicit of the potential. So in this case, it will contain basically gamma C squared, and this other gamma you want to keep it explicit, so put in an S. But it will also contain the Laplace operator, discretized, of course. So when you take A, you are just basically taking the diagonal of the Laplace operator plus this additional term here. So A will depend on C squared, to be precise. While H will keep all the rest, all the remaining terms. The important thing is that A should be positive. Now you will see why. Because when you substitute this back in the Canadian equation, you get an equation that looks like this. Might look quite complicated, but in the end, it's just a simple advection diffusion equation with a reaction term. So even if you don't have a flow field in your system, you still have an advection term given by the gradient of this A, this diagonal. which as I said depends on C squared. And you also have an effective diffusivity. So you end up with a second order equation, something very classic that you can solve in OpenFOAM quite easily. The algorithm is quite straightforward. First, you allocate the matrix. So M and S, in OpenFOAM, they are considered as basically as one matrix, because the matrix in OpenFOAM contains the actual matrix in LDO addressing plus the source term. And then you compute this U star, gamma, and S dot. So this effective velocity, diffusion coefficient, and source term, and you just solve this equation here. And then you have to reiterate in order to have the convergence of the nonlinear terms, and also the convergence of this H term, which contains also the off-diagonal components of the first Laplace operator of this. So it's a kind of an alternative way of discretizing the fourth order operation, keeping only the local stencil implicit as much as possible, and whatever is outside, kind of making it explicit. So okay, I tested these two different solvers for a very simple case, so a simple coarsening case. In this coarsening case, you have an initial field of C that is given by cosine functions. So it's a very basic perturbation, and you will have that the phases start to segregate. And if you run this case for different grids, you will see that there is little dependence on the grid, and both the algorithms are basically performing the same in terms of accuracy. However, must be mentioned that the coupled algorithm performs much better in terms of performance, for the simple reason that it requires less iterations to converge, since you are also solving for the chemical potential. So you are not really doing this trick of keeping some paths explicit, some other implicit, and it takes much less. I would say it takes half of the time with respect to a segregated approach. However, in many cases, you are not really interested in having such large time steps as in this case, or you are just interested in having small time steps and solving the equation just one time. In that case, then segregated approach could be better, as it is often done actually. Now we're similar to how interform is implemented, so solving the equation for the other parameter in an explicit way. In this case, it would be still implicit. And yeah, why did I choose 0.08 seconds? Because this system, which is a kind of temporary steady state at this time, and then at around 0.2 seconds, 0.25, start doing other things, so that kind of course. There are many scales in this problem. It is just the initial time step. Another test case ran is a classic spinodal decomposition. Spinodal in the sense that you have you have your system that travels towards the minima of the double potential, and you can see that starting from a linear profile of the concentration with some perturbations, you have the spontaneous formation of droplets and bubbles, if you want, or the structures. And you have three regions: one region of clear phase, another region of clear phase, and a region at the interface, where you have some coarsening phenomena happening. And if you let it run, the simulation run long enough, you will end up with a flat interface. Here I use a quite fine mesh, 512 to the power 2 cells, so quite fine. It runs quite fast because it's 2D anyway, and it was also multiprocessors. I just use 8 cores, and there are no issues running this solvers in parallel, so they work quite well in parallel. Another thing that is interesting to see, other than the nice picture and the effects of this coarsening, is how the free energy behaves in the system So you see that at the very beginning, the free energy decays. Now here there are no units, this is all dimensionless. The free energy decays very quickly. And then it starts decaying slowly, but you still have some regions where the free energy decays very quickly. Now you see that the behavior is different between the two algorithms. This is just because I use different seeds. The initial free energy is the same, but the seeds is different. So you have different regions where you have formation of bubbles and droplets. Here in log, you can see very well that at the very first time step, you have a dramatic decrease in the free energy, and then you have that it decreases more slowly. And this is related to what you can see here. So at the beginning, you have very fast transient, and then the things kind of become slower and slower. But if you look carefully, for example, here, you see very quick transients. You see that these droplets at some point disappear. They might remain of this shape for quite a long time, and then suddenly they disappear. So next, I want to discuss how these solvers can be coupled with Navier-Stokes equation. This is done in a very standard way, actually, in the same way in which interform is coded. So a Navier-Stokes equation, classic interform Navier-Stokes equation with a surface tension force that in this case is given in the phase field form, so as the product of the potential by the gradient of the other parameter. And I just use standard relations for the viscosity and the density. This is just the average of the two, total geometric average. So one thing I was particularly interested in is the effect of this on the spurious currents. And I saw that actually I was running some tests with the spurious currents when I found this article from the group of Marshall and Warner. Actually, they used the air phase field, which is completely explicit, and they obtained a very nice values for the spurious currents, very low. They got a picture very similar to this one that my solver can reproduce almost exactly. I can say. See that the spurious currents they create this vortexes, but the magnitude of the velocity is quite low compared to what you will get in interform. So this is a static bubble of air in water, 0.5 millimeters. So it's quite small, not excessively small. And it's the Laplace jump is quite accurate, just a 0.2% difference with respect to the theoretical value. So it's very, I would say it's very suitable for this kind of situations where you have a surface tension that dominates the dynamics of your flow, especially when you compare against interform. You see that there is a dramatic difference. So this is another case I was running with Dr. Giustini. It's another kind of bubble, 2 millimeter diameter. And you can see that the spurious currents of interform are much higher than those from the phase field model. So from the solving the Caniglia equation. So the blue is interform and red is the phase field. It's completely, say, a huge difference. And also the trend is different. And this is because at the very beginning, the field that I imposed for the phase field, it's not really the real final solution. So at the beginning, the bubble has to adjust itself to balance and to minimize the surface energy. Because for this, I used funky set fields to force an arcotangent field. All right. So getting the conclusions, I showed a new approach to solve the segregated Caniglia equation. So keeping some of the terms implicit as much as I can, I would say. And I show that this method performs better than interform regarding its previous currents. Now, what I'm doing right now is including models for phase change, taking into account evaporation, but also melting and solidification. For this, normally we solve the Allen-Kahn equation, which is another kind of phase field. It's a related equation. And yeah, that will be the future step. So thank you for your attention and questions if you have.
So thank you, Federico, for your talk. So you get some more clapping. I haven't found the soundtrack, but you get it live, which is much better. So I have some questions from Holger, and I'll start with those two. Many thanks, Federico. Have you tried other types of nonlinear potential models? How does the algorithm cope with double obstacle potential?
No, I didn't try any other kind of potential, just standard double well. The moment I didn't include any other one.
Okay. So Federico, could you please also comment on convex concave splitting of nonlinear terms?
Mm-hmm. Yeah, yeah, these are approaches using to split the nonlinear term, keeping different parts explicit. No, normally these are used for explicit time stepping. So a part of the potential is kept from the previous time step, and another part is adapted. In this case, yeah, the way in which you split the potential changes the convergence properties a lot, because of course it changes the sign of the matrix. In principle, you could keep all the potential somewhat implicit, so linearizing it, and keeping just the coefficients of the linearized potential, updating them in a Picard iteration loop, so classic way. But if you do that, you see that this term here, I don't know if you can see my mouse actually. I just assume.
We can see your mouse. Mouse.
That's great. That's great. So this term here of the potential is just -1. This is going to ruin the diagonal dominance of the matrix, and especially in this algorithm here, is going to make this A negative most of the times, because this squared is always going to be smaller than 1. So yeah, this part here should be explicit. So this is a kind of, if I remember correctly, like a concave or convex, they use this term. But what I do is just maximizing the diagonal dominance of the matrix. This is my approach for splitting the potential, which is different from what is normally done in phase-free community, because they look at other things instead of completely explicit time stepping most of the time.
So you do it as USP, yeah? So you look at the sign and then you put it into the source. In
a certain way, yes, but I don't need to do like that, because this term here is going to be always negative. Basically, the potential is given by this form here, which is not written. Let's say this form here without the Laplace term. So this term here is going to be always a negative contribution to the diagonal. Since I want to keep the diagonal of my matrix always positive, I just keep this term here implicit. So it will be a gamma c squared. So this term here. And this other here, I put it explicit, but then I update it in the next iteration, of next Picard iteration. So it's
so how many iterations? I was just wondering, how many iterations do you need on the outside of the block solver?
Yeah, that's a good question. It takes quite. It really depends on the convergence criteria, because normally what I check is the free energy, the potential, and the other parameter, and I fix some residuals on them. So when all the residuals are satisfied, then I stop. Depends also on the mesh size. In this case, I think I need quite many around. For the case with the finest mesh, I needed around 100 iterations to get convergence, all the residuals below 10 to the minus 5. And in this year, I needed less. I needed around 30, 40. However, the quantity that is lowest to converge, of course, is the chemical potential. So if you're interested in the chemical potential in keeping this value here, which normally is used for surface tension, if you want to keep a very good accuracy below, let's say, 10 to the minus 5, then it will take several iterations.
So every time I see something like that with a nonlinear term, yeah, and then I see people multiplying it just out, I just wonder whether it's if you do take the derivative of the inside and then split it, yeah. So like a fixed point iteration. I'm pretty sure you probably thought about that as well. It's going to give you the trouble with the sign as well.
Yeah.
So you need to do the stabilization, but at least if I look at the first, yeah, your derivative, if you think of it as a derivative, your derivative is wrong by a factor of 3. Yeah.
Yeah,
so if I think of it as a fixed point iteration, then basically your gradient is wrong. But all these considerations with positiveness of the diagonal, sure, I mean, you can't win. So, but this is just something, probably you thought about it, but this is just a pointer from my side to, yeah, maybe where some improvements can be made.
Oh, thank you. Yeah, we look into that, the kind of splitting to improve the convergence most of the other iterations.
Yeah, because the derivative of c to the power of 3 is, yeah, 3c squared.
Yeah, no, here
Not
I
c
just,
squared.
yeah, exactly. Now, in this case, I just take one of the c's and I keep it,
Yeah.
it's like a source term.
Yeah, basically,
one of the source
moving in the wrong direction, yeah. Okay, so what do we have here? Okay, so hi, very nice talk. So is the coupled method more accurate and faster, or just more accurate? And do you have some sort of adjusting parameter for the coupled method? If yes, how do you adjust?
Well, I will not say the coupled method is really more accurate. I would say it's faster, at least for the cases I tried. I wasn't able to make it work yet for the case where you have Navier-Stokes equation coupled, but it might just be due to the splitting of the potential. There are parameters to adjust it. Depends which kind of parameters. One, of course, is the mobility. So the mobility is just a parameter that's we have to enter in the model. Another is the epsilon, so the width of the interface. That's also another parameter. In the coupled solver, there is really no other. There is no big difference in parameters. Except in the coupled solver, you also need the boundary conditions for the potential, the chemical potential. So that's maybe the main difference between the two.
Okay, thank you. And we have very interesting from Abdul. What was the simulation time for spinodal decomposition? Also, is the code open source?
The code is not open source yet, sir. As I did not release it yet in my GitHub repository. This really depends how long you want to run it. If you want to run it till the end, it takes some hours. I never run it actually until the very, very end, because to make a video, then it will fill memory of my computer. But yeah, to run this, this specific video doesn't take long, maybe 10-15 minutes. Another thing I'm working at is an adaptive time step to speed up the parts where the free energy is varying more quickly and relaxing. So having larger time steps where the free energy doesn't vary that quickly. In that case, this kind of computations can be speed up quite a lot.
So how long did it take for the 512 squared cells 8 cores?
This one, and I think it took, for this particular case, maybe between 20 minutes and,
Okay.
I think it is, yeah, around 30 minutes.
Yeah, that's a rough idea.
Mhm.
Okay, and from Dragana, hi, amazing work. Do you have any available publication where one can get better insight? I think you've mentioned something on the last slide, or no?
Not yet. Actually, I'm in the process of. As you notice, there are some things that still need to be adjusted. One is the splitting of the potential, and another one is the adaptive time stepping. So working on that, but I'm counting on publishing very soon.
So there is a paper to come.
Oh.
Publication is being written. Okay, so I'm running out of questions. And so thank you very much, and let's thank our speakers again.
Thanks to you.
So thank you very much, all of you. I'll see you at the whiskey tasting, maybe, possibly, hopefully. So keep foaming and get connected and use the time to chat and engage. So thank you very much.